At CECO-Environmental, we're proud to be your single source for pollution control. It's our mission to protect our shared environment, and we relentlessly pursue that goal by providing reliable products and services to tackle your environmental challenges. Purchasing pollution control equipment can be a complicated process, particularly when you have a system that requires many different pieces of equipment. However, our vast range of technologies and solutions for pollution control and product recovery can eliminate that complexity, lowering your total cost of ownership without sacrificing performance. Across a wide variety of industries, CECO helps ensure you achieve real results. No matter your need, CECO has you covered. Simplify your environmental initiatives with our CECO-Environmental family of industrial solutions brands. CECO-Environmental is a global leader in air quality and fluid handling, serving the energy, industrial, and other niche markets. Through innovative technology and application expertise, CECO helps you grow your business with safe, clean, and more efficient solutions that help protect our shared environment. We work tirelessly to improve air quality, optimize the energy value chain, and provide custom-engineered solutions for applications including oil and gas, power generation, water and wastewater, battery production, polysilicon fabrication, chemical and petrochemical processing, and more. To learn more, visit CECOEnviro.com today.
Welcome, everybody, and thank you for joining us today for the CECO Certified Continuing Education Series. Today we are going to be talking about mist elimination fundamentals presented by CECO-Environmental. My name is Mary Rusnak, and I'm the Director of Marketing for CECO. And I'm glad to have two presenters joining me today, Damian Adams, who is our National Business Development Manager for CECO Filters, and Matt Lee, who is our Applications Engineer for CECO Filters. While we wait for everyone to join, I'd like to go over some basic housekeeping items about the platform and also about the PDH certification that goes along with it. So first of all, just sound issues, always one of the things that we want to touch on first. Hopefully people can see this slide and they can take a look, and you want to check that mute orange arrow button. Check to make sure that you're not muted. The blue arrow will take you to the help widget, and then obviously, if you log in and log back out, or log back out and log back in using that same email that you used to register, a lot of times that takes care of that issue. So at the bottom, we're going to talk a little bit here about the widgets and everything. So at the bottom of your screen are multiple application engagement tools, or widgets, that you can use throughout the whole presentation. All the widgets are resizable and movable, so feel free to move them around and do whatever you need to get the best out of your space. And all the windows that you have can be maximized or minimized to, again, work with whatever your platform is. So just take a look at those arrows on the outer corners, and you can move them in and make them larger and smaller. If you have any questions during the webcast, you can submit them through the Q&A widget, which is already expanded. To keep that ourselves on track, we're going to keep all the questions until the end of the presentation, but you can definitely submit those questions at any time. If we don't get to your question during this event live, don't worry about it. We reach out to everybody and answer your questions. So make sure to put them in there, and we will definitely get back to you. A copy of today's slide deck and additional help information are available in the resource list. And we encourage you to download any resources or links that you might find useful. Some of the things that you can also do in that area is you can basically go over to our LinkedIn, Facebook, and YouTube areas. We do post all of our events live on social media there. So if you want to keep up with any of the future events, that's a good way to do it by following us. There is a mist elimination summary in there that would be super useful to anybody that is taking the quiz at the end, hint, hint. Also, there is a PDF in there that talks about the states that we offer PDH credits for. Right now, we're able to do 36 states. If you hover over any of the widgets, it'll basically tell you exactly what they are. So just hover over them, and there's a lot of different options. You can share this event via social. You can email me directly. If you take a look at that check mark widget, that takes you over to CECO-Certified.com, where you can take a look at the rest of our schedule. We have, I believe we're up to about 10 events that are available on demand, and you can also see future events that are happening. One of the most important things, too, for anybody who's taken the PDH are the last two widgets on this, which is your test widget and your tracker widget. So the test one obviously is where you're going to take your test, and the track here lets you know if you've completed all of the qualifications that are required. So webinar is very bandwidth intensive. Make sure that you close anything that's unnecessary, just to make sure that things work well for you. If for some reason you are getting to the point that your slides are behind, push your F5 key on your keyboard, and that will refresh the page. We've also found that Chrome works the best for this platform. All of these answers and any additional technical issues can also be addressed through that help widget, so make sure that you use that if you need to. An on-demand version of the webcast will be available pretty quickly after the event, typically about 2 hours, and it can be accessed at any time using the same link that you used to come in today. All the interactivity remains, including the testing capability, so for any reason you end up getting cut off or you need to leave, you can come back and still complete everything. So let's talk about the webinar itself. Today's webinar is worth 1 professional development hour. You do need to be present for 50 minutes. We do have a quiz at the end that you need to complete and pass, which is getting 8 out of 10 answers correct. When you do pass all of these requirements, you'll get a little box that pops up that you can print your certificate. Definitely recommend that you all keep a log of this. That way that if any of your organizations, your state representative organizations want to see it, they will have that. We do keep our records for 6 years. And if you have any questions, you can email me directly with that email address, or you can use the widget that is below. The webinar is 1 hour long, but we're going to keep the platform open for an additional 30 minutes after the event. And we're going to do that really to allow people to complete the quiz and also to print out any other materials that they need to. So don't worry if we go quiet. You'll have 30 minutes at the end to finish up anything that you need to. Let's talk a little bit about what we're going to go over today in terms of the presentation. And part of that is, what is MIST and how is it formed? Why would we be concerned about MIST? What are some of the things out there that create MIST? And what are some of the things that can help you control that MIST? And then, really talking about some of the advantages and limitations depending on which version you're looking at. Looking at some design considerations, and then also what other processes are actually a part of this that, might be of interest for you to learn. Before we move into that, we are going to start with a poll question, and just like if you've been to our event in the past, you can answer the poll question in the upcoming slide. So how much experience do you have with MIST eliminators? And you have some options of I'm an expert, I have some experience, little experience, what in the world is a MIST eliminator? And this is where you can input your answer. And we'll give everybody a little bit of time to do this. All right, let's see what the answers are. It looks like it has not caught up yet in terms of poll. Let's try this one more time and see if, there we go. Okay. I don't know why it keeps popping back here. So here you go. So we have a good portion here, about 16%, that don't know what a MIST eliminator is. So don't worry about that. We're definitely going to help you out. And some who have had a little bit of experience, and maybe about 37% that have some experience. So I think this is going to be a great presentation for all of you, because it's definitely giving the basics and helping out with giving you that foundation to help you understand what this process is, how it works, and what you need to do to manage it. And I'm going to turn this over to Damien now, who is going to start us off.
Thank you, Mary, and welcome everyone. My name is Damien Adams. I'll be starting off the presentation. First, what is MIST elimination and why is it needed? MIST elimination or the removal of entrained liquid droplets from a vapor stream, is one of the most common industrial process challenges encountered. Unfortunately, mist eliminators are often considered a commodity item and are specified sometimes without thorough attention to operating conditions, available technology, and design approaches. The engineered mist eliminator provides significant utility, such as it aids in the capacity increases, reduces liquid carryover, protects process equipment, and protects the environment, just to name a few. Again, this webinar provides fundamentals of mist eliminator theory and design. Matt Lee and I are always available for your process-specific inquiries if you would like to learn more on how we can support your operations. In process equipment, when a liquid and a gas have been in contact, the gas leaving carries entrained liquid droplets. If the gas is traveling too fast to allow the liquid droplets to settle out under gravity, they become suspended or entrained in the gas or vapor. In most cases, the entrainment must be removed to purify the gas and prevent potential process or environmental contamination. This entrained liquid is also called mist. Mist is the suspension of liquid droplets formed when a finely divided liquid is suspended in the air or gas stream. Insoluble solids or particulate matter are not considered mist. Soluble solids, when wetted, becomes a mist. Gases and vapors are not considered a mist unless they are condensed. Mist generally ranges in size between 1/100 of a micron to 100 microns, or about the average size of a human hair, as you can see on this graph or this diagram. Unabated mist can cause production inefficiencies, employee safety issues, and pollution problems. Further, this entrained liquid can cause product loss, product contamination, and destruction of downstream equipment. Because of these consequences, this issue has received a great deal of attention. The way droplets are formed determines the size of the droplets. Knowledge of the mechanisms that cause droplet formation and the resulting droplet size is essential to proper mist eliminator selection and design. There are three common mist forming mechanisms. They are mechanical, chemical reaction, and condensation or thermal cooling. First, mechanical. Physical shearing forces break up a liquid to form an aerosol mist. Mists created by the mechanical means contain droplets that are larger and greater than 1 micron in size. In acid mist and other chemical processes, droplets are also created by the splatter and shifting of the liquid acid in the distributor and reactor towers. Droplets can also occur from bubbles bursting or jetting at a gas-liquid interface, typically in distillation columns, evaporators, bubble columns, and flooded packed bed scrubbers. These droplets become entrained in the upper gas flow, and if not abated, will cause downstream equipment corrosion and air pollution. The mist mean size in mechanical formation is equal to or greater than 2.5 microns in size. Chemical reaction. When two gases react to form a liquid product, large quantities of submicron droplets are formed, which in turn requires high-efficiency separation equipment. The chemical reaction of two or more gases can create mists correlated to their chemical composition temperatures, and pressures. This type of mist contains the most difficult droplets to capture, which are submicron sized aerosols. Several applications involve chemical reactions, from refineries to incinerators. Even small amounts of sulfur trioxide react with water vapors to form submicron sulfuric acid mist. These droplets create opacity violations and air pollution control hazards. In addition, the presence of mist within the process will impact product purity, increase maintenance and OpEx. The mean size for chemical reaction processes of a droplet is about 0.3 of a micron or greater. Condensation, or thermal cooling. When a gas stream is saturated with vapor and is exposed to a temperature drop, that cool vapor in the gas stream will condense to form a mist. Droplets formed because of cooling and condensed vapor are usually very small and submicron in size, or less than 1 micron in diameter. Organic submicron mist, also known as blue smoke, from plastic processing, vinyl curing, fabric finishing, and metal working, to just name a few, cause highly visible stack plumes and will result in environmental opacity and cause health and safety issues. The mean mist size is equal to or greater than 1 micron for thermal cooling or condensation applications. Applications that have entrained liquids do not consist of only one size of droplet. The average size droplet depends on the mechanism by which the droplet is generated. Sizing equations are expressed in terms of the probability of removing a droplet of a given diameter, and mist eliminator performance is the integration of individual removal efficiencies. It is critical to know the approximate droplet size distribution to properly design a mist elimination system. Because droplet size information for many processes is localized to specific plant processes, we will discuss generic droplet size distributions applicable to those processes. Air sampling and testing may be required to determine the droplet size distributions for your specific process. The concept of generic droplet size distribution is based on categorizing measured droplets from similar processes generating emissions from similar materials. These generic distributions have been developed from decades of experience and source data. Generic droplet size distributions are approximations. They should be used only in the absence of source-specific droplet size distributions. Many industrial processes generate mists that require abatement. This by means is not an exhaustive list of applications. Applications that primarily use oil and water-soluble lubricants, coolants, and detergents in their processes typically generate a mist and require a mist collector. These applications include, but are not limited to, metal cutting, metal forming, part washers, rotating equipment, lube oil systems. The mist generated in these types of applications can be categorized in mechanical and condensation or thermal cooling formation of droplets. The droplet size generated in these types of processes are typically greater than 1 micron in size. Processes that heat up or compress a liquid under high pressure typically generate a vapor that condenses back to a liquid when it is cooled and causes what looks like to be a cloud, also known as opacity. Some common applications that generate condensed vapors are machining hard metal alloys with oil, lube oil reservoirs on large generators, liquid asphalt applications, food fryers, plastic forming, exhaust from textile tender frames, plasticizer fumes from various heat curing operations, and other condensable hydrocarbon emissions from various industrial processes. Mist formed through the condensation mechanism typically generate droplets in the range of 0.07 of a micron to 3 microns in size. In the chemical industry, acid mist is generated by chemical reactions as well as mechanical forces and condensation. Typical processes include sulfuric acid plants, oleum storage tank vents, nitric acid plants, phosphoric acid plants, chlorine plants, fumes of sodium chloride, brine mist, as well as lead acid storage battery plants and other acid mist applications. The size and quantity of mist generated depend on the type of plant, the gas source, operating parameters, acid strength, the type of distributor or reactor. Typical droplet ranges are from 0.2 to 10 microns or even greater in size. The catalytic oxidation method of manufacturing sulfuric acid produces extremely harmful aerosols of sulfur trioxide and sulfuric acid. The droplet size distribution of the aerosols varies somewhat with the product being manufactured and the piece of equipment. For example, the droplet size distribution from the drying tower, the primary absorbing tower, and the secondary absorbent tower, as well as the ammonia scrubber, may differ from one another. The droplet size distribution will also vary with the strength of acid being produced. In general, oleum plants will produce aerosols of about 0.3 of a micron in size. In non-oleum production plants, typical aerosol is 1 to 2 microns. All of these plants can produce aerosols ranging from 0.2 of a micron to 10 microns in size. Finally, fine droplets, generally defined as less than 3 microns in diameter, are one of the most critical forms of air pollution. First, these fine droplets can remain airborne for extended periods. Secondly, their greater ability to obstruct and scatter light causes smog as well as haze problems. And most important, they are a health problem, since in contrast to larger droplets, they can bypass the body's respiratory filters and penetrate deep into the lungs. Several types of mist eliminators are available for the separation of entrained liquids. To choose the appropriate equipment, the basic mechanisms of droplet capture should be considered. Now, Matt will take over and provide details on collection mechanisms and technology.
Thanks, Damien. We are going to hit a quick poll question here before I turn it over to Matt. So again, same scenario here. Next slide is where you're going to put your answer. So are you currently using any type of mist elimination control at your facility? So yes, no, or it's really not applicable to you. So answer your question here. We'll give the system a little bit of time here to catch and tabulate all the results, and we'll take a look at it. Okay, let's see what some of the results are here. Okay, so, you know, quite a majority don't have this at their facility right now. So that's interesting, and it's good. It'll give you something to definitely, hopefully, be a useful presentation for you to understand what this is and see if there is possibly a use in your future. So I'm going to turn this over to Matt, who's going to continue with the presentation.
Thank you, Damien, and thank you, Mary. My name is Matt Lee. I've been with CECO Filters for the past 26 years, involved with many types of mist eliminators. Damien has also been working with mist eliminators most of his professional life. Hopefully you'll find this training useful, and we can give you a practical, concise explanation of what we believe to be the important points of mist elimination. And we thank you for your time and attendance here. We appreciate that. Everything we use and come in contact with, from water to food to energy, depends at some point on the separation of liquids from gas. Removal of droplets may be needed for purification or concentration or, recovery of the product. Or it could be, just for, air pollution control, or it could be a waste product, the liquid at the end, or, it could be useful. So what I'm gonna go over several types of mist collection mechanisms that you see on the screen there. There's many others as well, but that's some of the ones that we picked out that are very common and that we want to talk about today. Each of these mechanisms has their own advantages and disadvantages and specific parameters in terms of how they're useful or not. The simplest mechanism for mist elimination is gravity separation. You may be more familiar with the equivalent terms such as knockout drum or dropout chamber. This is simply a large open chamber. As the gas diffuses into the chamber, the upward velocity toward the outlet drops very low in comparison to the inlet duct velocity. The velocity is low enough that the droplets will fall downward due to gravity against the upward flowing gas. The larger the droplet, the more easily it can fall against the opposing gas flow. The balance point where the droplet would just hover, balance between the drag and gravity, is what's called Stokes terminal velocity. This is an important parameter in the design of gravity separation devices. This technology is generally useful for droplets larger than 100 micron in diameter. Of course, we are talking about since we were talking about two opposing forces, the drag from the gas flow and the gravity on the droplet, there are many factors that would affect the Stokes terminal velocity, such as the gas density, gas velocity, gas viscosity, and liquid density, and the droplet shape. Oftentimes, we talk about particle sizes and particle diameters. They're not always spheres. In fact, they're often not spheres. Oftentimes we're talking about with liquid separation and also with solid separation. It's the shape of the particle or the droplet is very important as well. As I'm talking about generalities and performance throughout this presentation, let's consider that I'm talking about air and gas, because there's if you're talking about a high pressure situation or there's a lot of parameters that can change. So when I talk about the generalities, I'm talking about ambient conditions. Air is the gas, and as I say, water is the liquid. Gravity separation is the least expensive, lowest maintenance method for gas-liquid separation. But again, as I stated, it's only effective on very large liquid droplets. These separators are very easy to clean and maintain since they are completely open. There is no turn-down limit. When I speak of turn-down limit, what I mean is how low the velocity can be as a fraction of the design velocity and have the separator still work adequately. So in this case, there is no limit. You can turn it down. The lower you go, the easier that droplet will drop out. A cyclone or centrifugal separator is basically a vertical cylindrical vessel which uses radial acceleration for separating the entrained droplets from the carrier gas stream. Because of the simplicity of construction, the cyclone is used commonly in many manufacturing and chemical processing industries. Generally, the lower size limit for the droplets is about 10 microns. Similar to the gravity separator, this is a preferred separation method due to its simplicity of maintenance and operation. However, unlike with the gravity separator, due to the cyclonic action with the fixed geometry, there are significant limitations on the turn-down ratio. Basically, you're spinning that gas around, you're whipping it around the inside of that vessel there, and it's designed to go at a certain velocity, and if you slow that down, then you're just not pushing it towards the outside, the droplets as hard, so it'll just not work at some point. Another mist elimination process that I don't have listed here that is important, I think, is Venturi scrubbers. In these devices, the gas stream with water droplets is passed through a throat section where the gas passes through a very high velocity section. In addition, an additional water stream is injected into that inlet such that large droplets are additionally present in the gas stream. So how does injecting more mist into the gas stream create mist elimination? Well, I'm going to tell you. The entrained mist is presumably much finer than the coarse mist generated at the inlet nozzle. As the gas accelerates going through the throat section, the fine droplets accelerate with it. However, the large droplets injected at the inlet have too much inertia to accelerate with the gas and only moderately increase in velocity. As a result, the small droplets impact on the relatively stationary large droplets. In addition, as the gas and the small droplets exit the throat, the reverse happens, and they have another chance to impact. And then afterwards, you have generally what I'll talk about later, a vane-style mist eliminator, or you could even have an open gravity separation chamber that I just described before to separate that large mist now that you injected into the Venturi scrubber. And now I'm going to talk about electrostatic precipitator. It removes droplets from a gas stream by using electrical energy to charge droplets either positively or negatively. The charged droplets are then attracted to collector plates carrying the opposite charge. The collected droplets may be removed from collector plates as dry material, as in dry ESPs, or they might be washed from the plates with water, such as in wet ESPs. The interesting thing about ESPs is they're capable of submicron mist elimination. This is a very interesting separation device, in my opinion, because there's no media or tortuous path to cause resistance to airflow. The droplets simply are charged, and then they're attracted to the plates, regardless of the size. So as long as the particulate gets a charge, then it's attracted and it gets collected, and like I said, very low pressure drops. So a very interesting system there. Very high turn down ratio. One significant downside to the potential is the potential for fire. If the droplets are flammable or combustible, you have the high voltage there of the from the plates, which can cause a spark so it can ignite and cause a fire. Now, inertial separators or vane separators. With inertial separators, the gas stream is forced to make one or more abrupt changes in direction. As the gas changes direction, the drag from the change in direction of the gas tries to pull the droplet in the same direction. However, the inertial forces on the droplet contribute to it going in the original straight line, same direction. If the inertial forces are significant enough compared to the drag forces on the droplet, it will impinge onto the barrier plate. As the captured droplet combines with other impinged droplets, it becomes a film. And as the film grows, it gets thicker, and then gravity pulls on it, and it runs from the veins and is collected. Since we are relying on the momentum of the droplet for collection on these plates, there are significant turn-down ratio limitations. So again, if you lower the velocity, if you take it down, now you don't have, if you just kind of creep through this mist eliminator, it's gonna go, the droplet's gonna go with the gas stream, and it's not going to be effective. So there's definitely a turn-down ratio limitation here. Inertial separators are not as open and as easily maintained as gravity separators and cyclonic separators, but they're still fairly open compared to their brothers, which we talk about in the next section, with the impaction, ground, and diffusion mist eliminators. I will talk about this a little later in the training. But what I'm getting at with the maintenance issues is I'm speaking about buildup of solids in the separator. That's really what I'm talking about. Although the primary purpose of the liquid separator is to separate these two phases, it is very common that there is at least some solids there as well. It's not, usually you're not just trying to separate water from air. There's some other junk in there too that you're going to have to deal with. Inertial separator, these devices can, for all of these devices, particularly the ones that are more open, like say the gravity separator, the cyclonic separator, you can use spray nozzles to impingement, high volume impingement spray nozzles to either rinse off, if it's a soluble solid, to rinse it off, dissolve it, or to just physically remove it by impinging it with a liquid stream. That can be done online or offline depending on the design. You just have to design for whatever the intent is. Another important, let's see here, going on time. Another important collection mechanism is interception. If a droplet is carried in a stream does not have significant momentum to break through the streamlines as they curve around the target, the droplet will follow the streamline around the target, except, however, if the streamline on which the droplet center lies approaches significantly close to the, I'm not following my notes here. So basically what you have is this is interception, and you're typically we're talking about like a mesh pad here. So with a mesh pad, you're traveling through a fairly open mesh area. You can see the picture on the top as a side view of a mesh pad. And so you have open volume there. You have these targets, which are basically the wires that are in that mesh pad. And similar to the vane separator or the inertial separator, this droplet will tend to want to go in a straight line. The gas obviously is forced around the target, the solid wire there. And the larger the droplet, the more it want to go in a straight line and hit the target. Now this is a more difficult, tortuous path, so it's going to be more efficient on than the vane style separator on a given size droplet. The turn down ratio on these are also, there's a limitation there. Not as much as the vane style separator, but there still is a limitation, a turn down limitation on these devices, because it is relying on the velocity of the gas stream it relies on that energy to collect the droplet. Just get a drink of water there. Lose my voice. All right. So for vanes and mesh pads, and I'm going to be going over some equations here, but don't worry about that. There's not going to be any questions on the equations. The main reason I'm showing these equations is just to show the parameters that are important and talk through them. So that's all that is. So don't worry about that. So when we're talking about a vane or a mesh pad, impaction or vanes or interception device, the velocity, the design velocity it's going to be equal to K, which is basically your limit. Your K value is your limit as to, in terms of, say, feet per minute or whatever the velocity is of that device. So you're going to design the mist eliminator for something less than that. What happens is when you go over that is you get re-entrainment. So you can envisioning the process now where you have this mesh pad and you have the liquid droplets coming through. It's going to get to a point where your velocity is so high that that liquid is not going to drain back against the direction of flow, and then it's going to flood. So that's really what the K factor is there. Now, it does have to do with the density of the liquid and the gas. As you can imagine, like when I talked about ambient conditions, talking about air and water. Okay, so that's what we typically think about in this type of situation. But you could be talking about high pressure steam or something like that, an application with high pressure steam, where there's not a whole lot of difference between the liquid density and the gas density because it's pressurized. So when you're talking about a situation like that, then you have to design a much lower velocity, or it affects your K value. And that's what's inside that radical there. That's why that's present, because that has an effect there on it. Typically, your vane style mist eliminators, the K factor is about 0.5 to 0.6. Mesh pad is about 0.3 to 0.45. An interesting, I think a very interesting setup to have is what's called it's a combination setup where you have a mesh pad followed by a vane style mist eliminator. And in that case, what you're doing is you're utilizing the high efficiency mesh pad for collection, and you run it at a high velocity, so you know you're going to get re-entrainment. And then you use the vane mist eliminator afterwards to collect the entrained mist. It has a higher capacity. So that's a very nice combination mist eliminator that I just wanted to mention there. Again, it's a mesh pad. In that situation, it's called an agglomerator, followed by the vane style mist eliminator afterwards. So just wanted to mention that. All right. So now I'm just going to talk a little bit about pressure drop. For vane style mist eliminators, you can't really go. You can, but it's not practical to go back to first principles to say, okay, look at this geometry. What's the pressure drop going to be here? And when I talk about pressure drop, I'm talking about dry pressure drop. Once you get water in there, it's going to be a whole different story. So basically, without going into a lot of detail, you're similar to like a pressure drop across a valve. It's going to be some constant times the velocity squared, which is common because you're in a turbulent zone there. So that's basically it. So nothing miraculous there. For a mesh pad, though, we do have estimations of pressure drop, and this is useful because then you can see what changes will have what effect on pressure drop. So I'll just run through a few of these here. You have your friction factor, F, which is really related to your Reynolds number. So let's say it's approximately 0.4 in a lot of applications with mesh pads. You have your thickness of the mesh pad. So obviously the thicker the mesh pad, proportionally, it's going to be that much pressure drop. So if you have 2 inches thick instead of 1 inch thick, it'll be exactly double the pressure drop. Again, just the dry pressure drop. And then you have something which is the mesh pad specific surface area. This is an important parameter in mesh pads, both in terms of efficiency and pressure drop. What it is imagine all those fibers that are there in that mesh pad. Well, how much surface area is in there in a given cubic foot? Well, that's a very important factor. So if you take a cubic foot of the mesh pad, how many square feet of surface area are present in that cubic foot of mesh pad? You can imagine if it's a very coarse mesh, it's going to have a very low number. If it's a very fine mesh, it's going to have a very high number. And just like with efficiency, I'll talk about in a minute, the mesh pad, this has an effect on the pressure drop. So the more area you have in there per square foot, per cubic foot, it's going to make it more congested, and so it's going to give that a higher pressure drop, and it's going to be proportional, approximately. And this is a model. This isn't perfect, so according to the model, it'll be proportional. It'll be proportional to gas density and the velocity squared, because we're generally in a turbulent region here. And the other one's epsilon cubed on the bottom. Epsilon is the mesh void fraction. Now, I've seen this a lot in the field where, I'm taking a look at mesh pads. Mesh pads are often used after scrubbers. And it's very important that they're clean. Oftentimes, I've seen them where they're not, and they're half full of solids, and at that point they're not working. So the cleanliness of a mist eliminator, especially mesh pad and vein, the same thing. You have to make sure they're clean, and what I'm talking about, Browning diffusion candles, same there. That epsilon value is cubed. That means it's extremely important. It also means that when you're manufacturing it, the crimping and the compression is extremely important as well. Droplet removal efficiency. I'm going to speed things up here a little bit due to time, but it has to do with the K value here. There's a lot going on here, and actually it's a complex calculation. So I'm actually going to just know that there are equations to estimate the removal efficiency for mesh pads that goes back to first principles that is useful, and you can see the parameters that are affected here. Now I'm going to talk about the last one, which is Brownian diffusion. Give me a minute here. Diffusion capture on a target surface by diffusion or Brownian motion is the mechanism utilized to separate very fine liquid droplets. Brownian motion is the continuing zigzag motion of fine suspended droplets in a fluid. And unless your eyes are closed, you're probably looking at that zigzag GIF right now. So that blue ball that's in that GIF represents your submicron droplet. So you can see it's getting hit and knocked around by all those red balls, which are gas molecules. Gas molecules are constantly bouncing around. If you have a large droplet, say 50 microns, the inertia the mass is large, so it's not going to be affected by that. However, for very small droplets, let's say less than 1 micron, the size it's still very much larger than the colliding gas molecules, but those random collisions are enough to cause the droplet or the blue ball to move randomly. Additionally, if the droplet were even smaller, you would see it even more dramatically. So what I'm saying is the smaller the droplet with Brownian diffusion mist collectors, the smaller the droplet, the more this random motion. So what's going on here? So you have we looked at the flow path. Now this small droplet has a very low inertia. So it's going. The mean path of this droplet is going to go around this target or this fiber that you see here. But in actuality, it's going to deviate due to this random motion from that path. And so what you're looking at is every time it comes across one of these fibers, it has a certain probability of being collected on that fiber. So what we're so what you need to have is this is why a Brownian diffusion candle filter has a thick media bed, so that it has a good resonance time inside there, because you have to have enough targets for that probability of it to hit one for it to happen, because we're counting on that random Brownian motion for the collection. And then similar to in the other devices, what happens is this droplet is very, very small. So it's not going to drain on its own. So these are, so it's going to coalesce as it combines with other droplets, and then it's going to drain from the filter as it coalesces and combines and becomes larger. Gravity will pull it down and it'll drain from this filter, from this candle filter. Okay.
Thank you, Matt. And we're getting to the end of the presentation here. We'll start wrapping things up, but real quick poll question. What types of mist eliminators have you used? I know some of you are not using any right now, but hopefully you used something in the past. So you have a couple options: vane mist eliminator, mesh pad, candle filter, electrostatic precipitator, or something else. So please put your answer into this slide. Okay, and give everyone another second so we can look here. Looks like it has not populated yet, so let's try this one more time and see if it'll, there we go. All right, it's taking a little slow today. So it looks like a good portion of our audience has definitely worked with the mesh pad and the electrostatic precipitator, but we definitely have a little bit of rounding out in the other areas with the vane mist and the candle filter. So probably about what we expected. Okay, Matt?
Okay, so I am going to wrap things up here. So this is just a diagram showing the flow through a fiber bed diffusion candle filter. It sits on a tube sheet. The gas flow goes in through the media and then out the top. These are other names for these. You don't see these. They're not as common as, say, vane style or mesh pad mist eliminators. So there's lots of other names for them that you can see here that involve the coalescing nature of it, the Brownian diffusion, deep bed, and so on. The candle term comes from generally you use fiberglass for the media, and they're cylindrical, so they look like a big old candle sitting there on the tube sheet. It looks like a birthday cake if you have enough of them. So these are all the design considerations that go into all mist eliminators, as you can see here. The inlet velocity pressure drop. This is an important parameter for most. It's important on pressure drop, but it's also an important parameter for all mist elimination devices. If you're going to a cylindrical, a centrifugal separator, you need to make sure you don't have turbulence at the inlet because you need to create that vortex. So you have that there. In this case, you need to make sure you don't have uneven flow due to turbulence through the candle filter. So the inlet velocity has to be low enough there because of that. That's especially true on mesh pads where your pressure drop is lower. The lower the pressure drop, the more important distribution is. So just because of the nature of the resistance, the lower the pressure drop, the more you have to be concerned about distribution. So that would be the inlet velocity, the outlet velocity, and how much room you leave there for it. Outlet velocity is important on most mist collection devices because you don't want to re-entrain things. Oftentimes your gas flow is going by a wet area of the device. So if you go too fast there, you're going to re-entrain. You could also, again, with mesh pads, specifically in Chevron, I'm sorry, he's trading and vane mist eliminators, you could have maldistribution because of that. Some of the outlet velocity. The solid particulate. So I talked about washdown nozzles there. So you want to, that's one way to take care of it. You can also use some other types of mist eliminators ahead of it that are more open and easier to clean. Use them in combination to protect the more vulnerable one. And one thing I want to mention is quickly, when you're dealing with a mist, you could be dealing with an organic, which has a vapor pressure, or you could be dealing with an acid droplet, which has an acid gas vapor pressure portion. So oftentimes a mist elimination will need to be in combination with two devices that work on the non-liquid portion of that. So in the case of organics, you have the thermal thermal oxidizers. So you can use a mist eliminator ahead of that, where the thermal oxidizer will take care of the vapor portion. And for the acid gases, with the vapor portion, that's an acidic gas, you can use gas absorption to collect that vapor portion there. So I think that's about all I have there, Mary.
Okay. Thank you, Matt and Damien. Really appreciate the presentation. It's a lot of information that we're trying to cram into an hour, so appreciate how difficult that is. And just want to remind everyone that you can download the slides PDF here. So if there are additional information you want to take a closer look at, obviously feel free to reach back out to us, but definitely appreciate everyone's time. So we're going to hit a couple questions here before I pull some of those up. Just to remind everybody, in terms of the PDH portion, you need to have been present for at least 50 minutes of this presentation. You do need to complete that test. And once you get to that point, if you take a look at the two tracker widgets that are on the bottom, that's where you pick up the test. And once you fulfill all the requirements, that little button's going to pop up that says you can print here, and you can print your certificate from there. So once everything's completed, that's what you'll need to do. I will keep the presentation live for 30 minutes after we go quiet so that everyone can finish all of this out. So let's take a couple questions here, and just give me a second to queue that up. Okay, so we have a question. You recommend the mesh pad before the vein eliminator. Why not the other way around to extend mesh pad life?
That's a very good question. And you do, that is a configuration that makes sense exactly for the reason that you said. I mentioned, and also for, well, I talked about at the very end with solid buildup. Sometimes you'll use something that's more open to preserve the life of something that's downstream. So definitely recommend it for that reason. The opposite direction I talked about was just so you could get a very high velocity through a mesh pad. But certainly for the reason that you're stating here, the flipping it around makes a lot of sense as well.
Okay, great question. Let me queue up another one here, and thanks, Matt. So what are some practices to determine droplet size?
Okay. There are EPA methods that go into a detail on a lot of the ways to do this. The one is, you can use a laser particle counter, a handheld one. They have different, accuracies. You could use what's something that's more complex. It's called a cascade impactor. But there's also some really practical ways to do it too. That you're not gonna match any EPA method. But if you're looking at what something is coming out of the stack, you put a piece of cardboard on the ground, and you see how big a droplet it mix on the cardboard. A very interesting one is in sulfuric acid, where they do a stick test, and they actually put a pine stick into the gas stream. And the neat thing about sulfuric acid is it reacts to make a black spot. So there's actually, it's often used where you put a pine stick into the gas stream and you look at the droplet sizes, and it tells you a little bit about what's going on upstream. Good question.
Thank you. Thank you again. Okay, let me just take a look and see if we have time for one more question here. Let me scroll through these and see which one we can answer fairly quickly. I think this one we could answer fairly quickly, so. What's the typical life expectancy of a mist eliminator?
It really depends. It could theoretically, go on forever, until they get plugged with solid. So you typically, whenever it gets plugged with solid, so it could be 10 minutes or it could be 10 years. But usually what it determines the life is either plugged with solids or it melts because it's exposed to too high a temperature, or it corrodes due to chemical attack. So it all depends.
Thank you, Matt. Yeah, and just everyone, I want to thank you all for attending our event today, and I want to thank Matt and Damien for all their hard work at putting this presentation together. There were quite a few questions we did not get to, so don't worry, we will reach out to you and make sure that those questions are answered. Just want to remind everybody that if you need additional training, we offer all of these events on demand, and they are at CECOcertified.com, and we do have 10 of them right now, with every one of them offering PE credits. So please feel free to go over there and take any of the courses in your, whenever convenient for you, really. We are taking a little bit of a break here in the summer for July and August. There will be no additional live events happening, but we will be back in the fall in September with at least 2 or 3 additional events. So stay tuned for that. We'll update that schedule soon, but all the on-demand events will still be there. And really just a reminder as well for everyone, this is the instructions for printing out all of the information that you need. We are going to go quiet now, but the platform will remain live until about another 30 minutes or so. Please feel free to reach out to me if you have any questions, and I just thank you all for your time, and I hope you have a wonderful summer. Take care.